I have to kind of stay here because this is where they get the audio on the Zoom. Is that right? I was kind of stepping away from it yesterday. Did anyone review that? Is the audio bad? No.
Is someone checking that? I can't check it.
It doesn't matter. It's fine. I'll try not.
Okay, she's the quality control here.
Right. No, that's fine. I just wanted to know not to walk too far away from the so that they can hear me. Okay. Where's the pointer? Well, I can't really see anyway. All right, and you don't see the. Well, we'll try without pointer and stay in front of this. Okay, so it says data reduction number 3. That is not the case. I'm actually 5. Oh no. No, but it's fine. Okay, so I'm gonna talk to you about some F tools and the NuSTAR software pipeline that you need to use in order to reduce NuSTAR data. And unlike XMM, I don't need a whole 30 minutes to explain to you about calibration files.
Because you are young.
Because, no, not because.
NuSTAR is young.
Because like NiSTAR and Chandra and everyone else in NASA land, we all have the same type of calibration files, and it's all called the CalDB. And that's really all you need to know. There is a calibration database, and you need to download that, and that's all you really need to know. But there are some extra things I will talk to you about. But so you already know where HERESARC lives. So there is at HERESARC, there is a specific tab that says NuSTAR. So if you go to that specific tab, you will find the NuSTAR CalDB and you can download it. And it is unfortunately quite big. I think it is maybe 800 megabytes. The reason for that is that our response matrices are quite large. And just as XMM, we keep everything. That means we have all the rubbish and we have all the old response files, and it just keeps growing in size. So unfortunately, it is large. If you don't have it, I'm sure there are people here who has the CalDB for NuSTAR, and they can just give it to you on a stick. So when we get to that point and you don't have it, and we'll find out how to get it to you. Okay, so I'm going to say a little bit about the CalDB. This is the only thing I'm really going to say about this. So there's a CalDB structure when you open it. There's CalDB, there's data, and then you'll have all the missions. If you have different missions, Swift, NiSTAR, NuSTAR, Chandra, they'll all live in that layer where it says NuSTAR. They will all be parallel to each other. So for NuSTAR, then you have FPM, which was focal plane module. And in that directory, you will have a linked file called CalDB index. There will also be a folder there that's called index. And inside that CalDB, inside that index, you will have all the CalDB index files, which is a file that tells the pipeline which CalDB files it needs to get. And so if you want to go to a different CalDB file, let's say you downloaded the new one, but you are comparing data or you're comparing data from someone who has done a reduction with a different CalDB date, you can go in there and you can then link your CalDB index to that specific CalDB file that they used. So unlike XMM, each release has a number and a version number, which means you can easily find out, or not easily, but fairly easily, you can find out what set of calibration files did the other person use, because they'll give you the index file number. And so by doing the link, you can reproduce exactly what they did by changing where that CalDB index file is linked to. Okay, enough about CalDB. So observation ID. So NuSTAR has observation IDs, and it's an 11-digit number, as you see there. And there's really only 2 numbers you need to pay attention to. You don't even need to pay attention to the very first one, which is the C. So that number out there, and you can probably not read the small print, but you can just do that at your own leisure later on. That first number tells you what type it is, whether it's cluster, whether it's an X-ray binary, whether it's a galactic source, extragalactic source, AGN. So that's what that first number. In this case, the 7 means it's a cluster. Then the other set of numbers you should pay attention to is that very last one, 002. It's a sequence ID number. And for that particular source, the first time you go to it, the slew to it, so from wherever you were before, and you slew your instrument all the way over to the new source, that maneuver, that slew maneuver, is called 001. Then the actual observation itself is the 002. If I came back to this source again, let's say I went off and I observed another source, now I want to get back to that one again. The slew back to it would then be 003, and the observation would be 004. So you will see some of the NuSTAR data will have very long, they'll have 022, 024. So that just means it was observed not 24 times, but half of that. So it was observed 11 times. Sometimes, very rarely, there are a couple of these, the slew is not the uneven number. Usually the slew would be the uneven number and the observation would be the even number. In rare occasions, it's not the case. So when you get a data set from NuSTAR, you will get two, you will download the data and it will have two folders in there, and it'll have two sequence IDs. The one that's the lower one will be the slew, and then the next one will be the actual data. File structure, you cannot read that, so I actually zoomed in on it. So when you get the data from NuSTAR, let me see, how bad is this? Can you actually read any of this? Okay, you can. Great, good. Okay, so this is sort of, so that's what I told you right here. You can see the two numbers up there at the top of the file structure. You have a 001 and you have a 002. So that's your slew and your data. So inside the data bit, you will have three directories. You will have auxiliary directory. The auxiliary directory contains attitude file that tells you where you're pointed. It also tells the pipeline. For example, were you in the South Atlantic anomaly? Were you occulted because you were looking at the Earth? And it has other things in there too. Then there's an orbit file. Orbit file is a little more spacecraft oriented. And then you've got the next one, which is a 2-line element satellite position. You never need to worry about that, except on rare occasions, you will have two of these TLE files and you'll get an error when you run your pipeline. It just means delete the oldest one, just keep one, because it's automatically going to look and it finds 2 and it goes, I don't know what to do about 2. Just delete 1. Then you have the event _UF, which is unfiltered, stands for unfiltered. So this is the raw data as it comes down from the spacecraft. Nothing has been done to it. It's like one long sequence of just the detectors being on. You can actually look at it. You can look at it with DS9, but it has SAA, it has occultation, so it's not a useful science set. It has to be filtered first, and that's what the new pipeline does. Then you've got the housekeeping file structure, and inside the housekeeping, there are a lot of different things in there. You don't really need to know a lot about that, so you can read at your own leisure what's in there. So just remind you again, the anatomy lesson of what does a NuSTAR image look like. So it's not a huge detector. It is composed of 4 detectors, and they are called 0, 1, 2, 3. And they're organized, as you can see there. So it goes counterclockwise, and you start up at detector 0, and detector 0 is our best detector on both focal plane modules, and that's where we put the source. So that's the sweet spot. So that's where you should have the source. You can see occasionally, and in this particular case, the source actually extends over to the other detectors, and that's perfectly fine. But sometimes if the core of your source actually sits on you can see there are gaps, you might not get quite an accurate flux estimate. So just be aware of that. If your flux estimate for some reason looks weird, you can always go look at the event file in DS9, switch it to the coordinate system that says detector 1, and you can have a look and see where it actually is. Okay, so I think that's about what you need to know that. So then another useful thing to know about NuSTAR and keep in mind is the conversion between pulse invariant channels, because sometimes you will have to input into the pipeline these numbers in pulse invariant channels as opposed to being energy. So this just shows you how you convert from the PI channel into energy. And so 3 kV corresponds to 35 channels, 78 to 1910 channels. Okay, so there's a pipeline. This is very small and you can probably not read it at all. Yes, this is completely unreadable. So what you need to know is, in the same way that Jeremy talked about and everyone else, there is level 1 data, there's level 2 data, and there's level 3 data. So level 1 data, that's the raw spacecraft data files. That's what you get when you first download your NuSTAR data. Then you have to apply the pipeline, and it's called NuPipeline, very ingeniously. That then turns it into filtered data, but you can actually start doing science on. And then level 3 data is your higher level products, your light curves, your spectra, and so on and so forth. Okay, so there's a couple of, so here are just some links. There's a software guide. It's like a quick start software guide. You can go look at that too. There's just a link for that. And then the important tasks that you really do when you do NuSTAR data is the first thing you do the new pipeline. I should actually point out that when you, so I brought the NuSTAR data here, brought it here, and that actually has processed data in it. It already has level 2 files in it, but that is cheating. You have to do it from level 1 to level 2. So, and I actually think when you get the data, if I'm not quite wrong, if you get the data from HereStart, you will also have the processed data when you get down. That is sometimes okay. If you want to do a quick look, you can use the processed data, but it was often processed, you know, when it was delivered to, for example, year 2 is when a data set was delivered. That's 6 years ago. And we processed it with whatever CalDB files were at that time. Now it's been sitting for 6 years in the data archive. You download it. The calibration has been updated since. So you have an old version in there and it's really not updated. So you can look at the data, but we've since then done some updates. So it's really good. It's good practice to just reprocess your data using the NuPipeline command. And I'll do this step by step. I'll actually walk you through how to do this. So the first thing you do is you do NuPipeline to your level 1 data. Then you do new products. So once you have the data products in level 2 format, you can now start extracting spectra, and you do that with the new products command. And there are a couple of other ones. There is new makes light curves. I'm not going to read them. They're little. So they have new core, new LC core, which does light curves. It is better to do light curves using this this task than it is using, for example, there is XSelect. You can do light curves in XSelect too, but they're not accurate. So you, in order to get the correct corrections in there, you need to use the light curve procedure that you have in NuSTAR. Then there's something called NuSplit SC. I'll talk about that later. And there are a couple of other commands that are useful, especially new exposure map. If you're doing extended targets, you'd have to know about that. Okay. So data reduction. Mm-hmm.
Yeah, sorry. Can you elaborate why it is better ULC code than new products?
Yeah.
New products also give vector, right?
So new products gives you something, but it is you can use new products, but then you need to. There's a lot of settings. You'd have to go the right bin size, whether you want to have off corrections in there. And all, if you are aware of that, you can use it directly through new products. But let's say you don't want to redo the new products, you can just run the new LC core without running the new products.
So there is no inherent problem with running through new products, right?
You do not, there's not an issue running new LC core through new products. You can do that. You just need to be aware of all the settings. It's a little more transparent in new LC core what the settings are, but you can do it through new products.
Which is a convenience thing, not a.
It's not a convenient, yeah, it's just a convenience thing. And also if you want to run multiple LC cores, you don't want to run new products over and over and over again. You just want to run the new LC core. So it's just so convenient. It lives inside new products. It will call that if you run it through new products. Okay. So you can always look at fhelp new pipeline. That gives you all the parameters that you need to run that particular task. But here is an example. So new pipeline, this is just an example, and you can read that again at your own leisure. So I just want to point out there's some extra keywords that you may want to work with when you do the new pipeline. One of them is this ops mode, which in default is equal all. So what ops mode does, and this is the thing I mentioned briefly, that inside the attitude file, it knows whether the observatory was slewing, whether it's doing science, whether it's in the South Atlantic anomaly, whether it was doing calibration, or whether it was pointed at the sun and was missing a star tracker, which is this mode 6, which I'll talk about later. I kind of told you a little bit about it yesterday. So if you're in a situation where you have no star tracker and you just want a specific of these, you'll have to look at this ops mode. Then the other one that is very important to know about is this called SAA calc. So I told you yesterday too that as the instrument gets towards the SAA, we have an anti-coincidence shield that starts detecting a lot of particles in it. And at some point it gets high and it flips a flag that says you're now in the SAA. But it actually reached the SAA before the flag flipped off. So if you want to change that, if you want to change and remove more of the SAA, you can use this SAA calc. And I'll get a little bit into detail later where you can tell which one you need. There's 1 and 2. There's also,
Oh, yes. Yes, I knew why.
It's 2.
I wanted to finish that.
Yeah. Yes. So I can keep going because this is SAA. So the South Atlantic anomaly is an interesting thing. So it sits around the equator and we go through it. And it is a blob, it's uneven, which means as we go up and down, so we're not always at the same angle. We don't hit the SAA at the same latitude every time. So that means that changes all the time. And that's why we have tools, which I'll show you once we get the power back. There are tools which then tells you it'll tell you, you can see how badly the SAA is and whether you need to do something about it. And with that, I'll leave you hanging.
Why does the South Atlantic anomaly move around?
So it depends on, it's the magnetic field, it's trapped electrons. It's
topology of the field, it's just the population of charged particles.
Yeah, so if the sun is doing something, it'll grow brighter, I told you about this tentacle, it'll grow a tentacle. So depending on what happens with the sun, and you'll have it move around. And on top of that, we are not hitting at the same altitude every time. We're kind of going in and out. It goes up and down too. So I don't know if I'm still. I don't think we lost internet, did we? We're still on Zoom. Okay, the screen share just stopped, but I'm still on. I still see it. So you know how to do this?
Even we can see your screen.
Okay, so I can start it again. No. Okay. It's back up. Okay, yeah, so there's this SAA calc 1, 2, there's SAA mode, strict or optimized, and there's this tentacle. And then the other thing, the other extra keyword that you might want to play around with is this ARF MLI correction, yes or no. So I told you yesterday that it is temperature dependent, and it is kind of, sometimes it opens up a lot and suddenly you have a lot more flux coming through an FPMA. And there's only a handful of these targets. So the RF MLI core equals no does not apply a temperature dependent correction. But if you have one of these rare sources which have a lot of it, you have to activate that. And there is, and I forgot to put that in here, there is a web page which shows you which targets you have to use it for. And so you have to go check and see if your target is on that list. Okay, so to look for the SA calc, SA mode, and tentacle, which one you need to apply, or whether you need to apply it at all, you have to go to this link. So it's our NuSTAR SOC, so Science Operation webpage. There's a link there, and there is background filtering reports. So you can go to the background filtering reports, and there's a long description of what's in there, and then there's all of your ops IDs, all of the NuSTAR ops IDs are there, and you then find your source by the number, and then you can click on that, and then you get something like this. So that shows you latitude and longitude of the NuSTAR track as it's going across the Earth. And in this case here, you can see these enormous spikes in the top plot, right? The top plot there, you can see some spikes in that light curve, which you see on the left, those light curves. And if you go look at the tracks there, you can see you've got the red stuff right next to the SAA. So the SAA is the part that's been removed from those tracks, and you can see they're red right at the edges. This is just the SAA not being cut off. So by applying, you can see there's SAA. I can almost not read it here. Tentacle no, strict. You can, so if you by applying the SAA calc 1 strict, you can remove those bits, the spikes in your source. So you can go look at that. And then there's the tentacle. So the tentacle, we rediscovered it. It was apparently known in the 60s about this, and everyone forgot about it. And we went back up and rediscovered that there's a tentacle that sticks up from the SAA. And sometimes it's there, sometimes it's not. So we have a little flag that says tentacle, yes, no, and that'll then remove your tentacle from your data set. And someone called it tentacle because they used to play computer games and they thought that looked exactly like that Day of the Tentacle. So the name stuck. That's what it's called. Okay, so you run new pipeline and you get a bunch of outputs. The only ones you really need to worry or care about are the two in red. So you'll get one that's called new blah, 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 the sequence ID A01 underscore cleaned event. So that's your actual event list now that's cleaned, it's filtered. And the 01 you see there, you see A01. If we go back to the mode, this ops mode, the 01 corresponds to the science mode. That's why it says 01. You'll sometimes see 06. If you have something that says 06, that means you extracted it in this mode 6, where you have no star tracker at the front. And so you've got two of these. You've got A01 clean event, and you've got B01 cleaned events. Those are your two files. So here's just a slide that just tells you what each of those files is. I'm not going to go into details. You can read it again yourselves. So one thing that's interesting for you to do is to use the FV, which is the FITS viewer, and actually have a look into the event files themselves. So if you do that FV, the name of the cleaned event list, you'll get this. And you can go look inside it and you'll see that there's all sorts of things there. There are raw X detector ID. Detector ID means which detector did the event occur on. You should see most of them be in detector 0. So this is an interesting thing for you to look at. And there's also coordinates over here. You can see det1x, det1y, det1. Remember, that's the coordinate system on the detector. And then you'll see det2, which is an intermediate coordinate system. And then you'll see sky. Sky is in sky coordinates. So this is what it looks like in sky coordinates. This is FPMA and FPMB. They look pretty similar. They should look pretty similar. You'll see they're slightly different location on the detector. B will be slightly off from A, and if you look at the coordinates themselves, you may see up to 8 arc seconds difference in the coordinate. And that's perfectly normal. Don't freak out about it. Just know that it is, because if you no DS9, and let's say you put down your extraction region on FPMA and you just copy it and drop it into FPMB, it may be off. So just be aware of that and just do them independently so that you don't have that issue that you're.
So is this detector plane coordinate?
This is sky coordinates. This is in sky coordinates. So this is the projection on the sky. This is why you see it tilted. So that's the PA angle, and it's been adjusted so that you have a point source.
So this 8 comes from the calibration mismatch.
Hmm?
Why does it 8-second thing come?
So 8 arc seconds. So there is, we have a laser metrology system that tells us how the thing moves. And it's not, there are things on the bench that breathe because of thermal expansion. And sometimes you have that. It's just the accuracy of the reconstruction error. So here are again the coordinates. So if you're in DS9, it's be interesting to look at detector 1 coordinate system. That's where you have there. Then you have the intermediate, which it has applied the mast motions to it, and finally it has applied the spacecraft jitter motion, and now you've got a point source back there. Okay, so let's talk about source and background regions. So when you have NuSTAR data, you have to kind of distinguish a little bit between, it's a little bit different what you do for a bright source versus what you do for a faint source. Now, in general, the rule of thumb is that you should be taking your background region from the same detector. So there's 4 detectors, and you should try to take your background region from the same detector. And the reason for that is that very often your background is instrumental. And each of the detectors have a slightly different instrumental background. So by taking the background on the same detector, you should be having the same instrumental background. If you take your background from a different detector, your instrumental background will be slightly different. That's just the unfortunate thing about that. So you want to make, if you have a faint source, like in the case on the left, the faint case, you take a background region that is as large as you possibly can, as close as you possibly can to your source, because remember, there's also a gradient of background across the detectors. It varies across the detector. So you want to be as close as you can to that source. And so extracting how big should your extraction region be for your faint case? That is, you have to play around with that a little bit, because the larger you do your extraction region, the more background you're collecting as well. So sometimes you shouldn't be making it too large, because then your background is higher. You might just want to make it, I usually look at the logarithmic, and then where I can see the extent of the source, I put it a little bit further in than that. I don't want to be collecting more background than I'm collecting source photons. In the bright case, as you can see there, the source is completely contaminating one of the detectors. So you cannot take your background next to the source. You have to take it from another detector. And that's just what it is. But then you should know your bright source is going to be pretty good up to a certain kV. It just means that where you hit the background, you might not get it quite right, because the internal background is a little different. So you need to back off a little bit from that. You know, when you set what is your energy range where you want to fit it, don't go all the way out to where your background crosses. Go a little bit back from that, because your background is a little off. Yeah, so how can you tell? So you have to play around with stretching in DS9 to figure out when you're free of the source. So you can do that in different ways. You can switch the color, but so you have to look at it very carefully to see how far out does that source reach before you can have a clean background region. And again, you should try and make it as big as you possibly can, but there are diminishing returns. If you make it too big, you start collecting photons from the actual source. So that's something you just have to play around with a little bit. So here's the background again shown. So here you see that pretty much above 20 kV, your dominating background are instrumental background lines. So if you're above 20 kV, that's when you're in the instrumental background regime. Below 20 kV, your dominant background comes from the sky itself. It's called aperture flux. Nothing much you can do about it. And that particular aperture flux, that's the one that causes this gradient across the detector. So if you have if your background and your source dies out somewhere in the 20 kV, below 20 kV, that's where you want your background region to be as close as possible to your source, because you have this difference in the background. So you can go read that Daniel Wick paper. I have the link here to just get more details about the background. So if you want to have a couple of pointers, bigger region means more counts in terms of background, which is not always good. Sometimes smaller is better, but too small, you lose quality, because if you got too big, you start collecting stuff from other detectors. And so actually another thing, you don't want to have a background region straddling two detectors. You either want to be in one completely. So you can't do too big of a background region, because then you're straddling different detectors. You can't go too small either, because then you just don't have enough statistics in your background. So the other thing to know is that source extraction regions can only be circles and annuli in NuSTAR. You can't do squares, but your background regions can actually be squares and any shape almost. All right, so now you know a little bit about now you know how to do your extraction, you know where to put your backgrounds. Now it's time to actually extract the spectra. And so you do that with the new products. And again, if you type fhelp, you'll get all these, you get all the parameters that you can use with that particular call. And you'll see if things don't have parentheses around them, that means you have to give them that input. If it has the parentheses on it, you don't have to give it that input, and then it'll show you what the default is. And you actually, what you just do is see, no, it's not here, the LC core. For example, you can run the LC core inside new pipeline. If you look through that parameter file, you'll see the brackets around LC, something called new LC core. So here's an example. This is the minimum that you need, the minimum inputs you need to run the new products. And there are a couple of things that I like to add, and that is off-axis histogram file. And I like to add the off-axis file. That tells you, that file as a function of time will tell you how far off-axis you were. It's useful sometimes if something strange is happening to the source, you can sometimes look at that file and understand if you were very far off axis or very close. So it's a useful file to have. Actually, here's the light curves. I forgot I put this in. So if you want to run the light curves through new products, this page gives you all the instructions to do that. So a couple of things to know is you have to set your energy range, and you don't do that in energies, you do it in PI channels. That was why I gave you the PI channel conversion. Then there are corrections because of the effective area that you apply, and so you have to set it, you have to tell it at which effective area, which energy does it have to apply the effective area correction. And the default is 10 kV. Now we're back in kV, not PI. Very important to remember. And that's usually a pretty good number, because that's where the NuSTAR effective area peaks. It peaks at 10 kV. So to do it around that if you just do the entire range, 10 kV is where you have most of your photons. If you're doing a light curve at 40 kV to 60 kV, you do not want to do it at 10 kV. You want to do it at 50 kV. So just be aware of that. Okay, so new products, there's some other things, extended ARFs, extended sources. So if you have an extended source and you want to apply an effective area to that, you have to use the extended ARF feature in there. And there you have to set again, you have to set the energy range that you want to have it apply it to. You want to set how big. So what it's going to do, it's going to take the source you have, so your extraction region of your extended source, and it's going to make it into boxes. You have to give it the box size. If your box size is really small, it's going to take forever. If your box size, so you can see the default box size here is actually 20. That's in pixels. So I'd say you can go down to 10, 5, it starts getting really, really, really slow. You probably don't want to go any bigger than 20. So there's those, and then you can apply user GTI. So if you've looked at a light curve, yes. It has, you can apply the barocentric correction in there. Yeah, I guess I copied that. Yeah, so there's specific, so if you're doing timing analysis and you have a pulsar, the barycentric correction happens inside new products. So you just pay attention to that. So use of GTIs is if you have a light curve, and you can do this in X-Select, you pick these good time intervals, that's what GTI is. And then you can save a file and then you can feed it into new products, which means it will only pick the times that you want. Okay, so you run new products and there's a couple of standard outputs it gives you. For example, it gives you a light curve in specific, I think it's 100 seconds. It will give you a default light curve. It'll give you the spectrum, and it'll also give you a file, an actual image of the source, which is a GIF, just a GIF file. So these are sort of it'll just do that. You won't actually use, I mean, no one ever uses a GIF file. We just do it. So here's the effective area. Matteo mentioned that as a function of off-axis angle, it changes. So that's why if you have an extended source, you need to know about the exposure map. So what the exposure map does, it tells you how much time each part of the detector spent looking at a specific off-axis angle with a specific time. So because NuSTAR can be moving about, you can see in this case, this is not a perfect square. It actually has two offset squares because the pointing moved it over. So in sky coordinates, your detector moved a little bit over. So not all pieces of the sky have the same exposure. So that's what this particular tool allows you to calculate the exposure map. And there are instructions for doing that. I don't want to go through that. So there's some non-regular NuSTAR reductions. So let's talk about mode 6. So mode 6, so there were these different modes. 0-1 was the science mode. That's what you usually have. 0-2 is occultation. 3 is slew. 4 is SAA. 5 is calibration source. There's a calibration source that can come in and out. Use it very rarely. And 06 is the spacecraft science mode, which is when the front of the spacecraft is pointed close to the sun, and Q4, camera head unit 4, is blinded. So when that is blinded, we are missing this part. We can't do the sky projection with, we don't know exactly how the front end moved with respect to the sky. We only know, imagine you're a dog and you're at the tip of the tail, that's where your instrument is sitting. But you only know where your dog is because all your instrument, all your star trackers, all your the two camera unit 1, 2, 3. These are star cameras that sit on the dog and tells you where the dog is. But the tail is wagging around, so you need an additional sensor on the tail of the dog that tells you where you were with respect to the dog. You're missing the sensor on the tail, so you only know where the dog is, and this is why you get this smeared out image, because you're missing the sensor on the tail of the dog. So we use this. So why do we use it? We use it because sometimes bright transients go off very near the sun, and we're the only ones that can go look at them. Everyone else has the same issue. Many of the other observatories have the same issue. They have low energy detectors that can't go close to the sun, but we can actually look at the sun. So that's why we do this, even though we don't get perfect data out of it. We can deal with it because we've got this mode 6. And what mode 6 does is it takes, so you can see there's these 3 camera head units, 1, 2, 3. And depending on how you're rolling, either you're just tracking off 1, or you're tracking off 1 and 2, or you're tracking off 2 and 3, or 1 and 3. So there are combinations of these camera head units, and because they're not perfectly attached to the spacecraft, they jerk it around. So that's why you see it jump around these different, you see in that plot, you can see it just moves around when it goes to a different camera head unit. So what we can do is we use this NuSplit SC tool, and what it does is it allows us to then divide the data into each different camera head unit. And at that point you can do, so this is like new pipeline. At this point, you can do new products on each of these files individually and get exactly the same data out as you can from just normal data. So I talked a little bit about the stray light. We talked about that yesterday. So here are some cases. Most of the time we try to not put the source inside the stray light. Sometimes it is unavoidable. And in that case, we try to put the source entirely inside the stray light, because having it halfway on there is the worst case scenario, because what do you actually have in there? So if your source is entirely in the stray light region, your background has to come from the stray light region. If your source is outside, of course, don't take your background from the stray light region. So there are other ways that we have another tool called NuSTAR background. So in the case of this is an extended source. I actually think this is coma, if I'm not mistaken. It contaminates the entire detector. You cannot really get a proper background out of that. We have something called NuSTAR background tool. Here's directions to go to it, and that will allow you to actually get a background underneath it with some restrictions. Something else to know is X image. So if you want to do mosaics, you can do that with X image. This is actually the galactic center mosaic. And here are instructions for doing that. And in that case, it's very important, if you want to do some of this with exposure maps, you have to do the exposure map and also feed it into this. And then you get this very nice image, as you see up there, where everything has been exposure time corrected, and you get this beautiful sky image. So that's what you do with X image to get the mosaics and apply this exposure maps. So other useful commands, I'm gonna skip those just because you can read them yourselves. These are F tools that help you do a little bit of, you can change some header keywords inside the files. You can also combine some files, so you can read that on your own. So what I want to spend the rest of the time doing is I want to walk you through an example, a very complicated example in NuSTAR land, but I proposed for this with XMM several years ago, and the plan was we were going to use it as a calibration source because it has a big dust scattering halo. And I told you yesterday there was an issue. We want to understand with the dust scattering halo, why do the sources not look the same in XMM, in NuSTAR, and in Swift? So the plan was to observe GX 13+1 because it has an enormous dust scattering halo, do calibration on it. So we took all this data, and it turns out it's complicated. So there's a lot of stuff in there. So I'm just going to walk you through some things that I did with it and to show you what kind of data analysis you would do. So it's a low mass X-ray binary. It's got this dust scattering halo that you see over there. This is the V44 sig. This is the V44 sig, but it has a similar dust scattering halo. It is not changing in time. The reason the V44 sig looks like that is because it had pulses. So it got really bright, and then it got dim. It got really bright. It got dim, really bright. So that's why it has rings. GX 13+1 is a persistent source. So for it, the dust scattering halo is just a smooth. It just makes it a bigger. It just has a halo around it that's evenly even in intensity. So the diagram shows you what happens in dust scattering. So there is a sheet of dust somewhere between you and the source, and that dust sheet causes the X-ray photons to change direction. They just scatter off a bit. And depending if that sheet is closer, the closer that dust sheet is to you, the bigger the halo becomes. The closer it is to the source, the smaller it is. So you can use that actually to figure out where the different dust are between you and the source. And typically there are more than one. So that's why this is an interesting source in that respect. And by doing that, you can also figure out what is the grain size, what's the type of grains that are causing the scattering. So yeah, so it's a low X-ray. It's also a type 1 burster, which means that it's accreting Roche lobe overflowing from a star, and as it accumulates on top of it, at some point there's a thermonuclear burst, and it does a burst. So that's the type of source we're looking at. So it's a persistent, it is somewhat variable, and it has an enormous dust scattering. So it's about as complicated as you can get it. So the first thing you do if you have a data set like that, you go look at the background. So I told you I've got this dust scattering halo, and this plot you see down there in the left corner, I guess that's left corner, you see how, so I've taken annuli. Actually, actually, it's not an annuli, it's a circle, and I've just increased the circle and extracted the spectrum, increased it and extracted. And what you can see when you then plot all of them on top of each other, that there is more low energy photons further out in the wings than there is closer to the source. So what happens is that the low energy photons get scattered into the wings, and at some point that you can see, that's about 7 keV, the dust scattering halo is gone. So at low energies, you've got a huge difference between which size, depending on what the size is of your extraction region, your spectrum looks different. So that's what the dust scattering does. So the first thing I had to go look at is I got to figure out what background to use here, because the dust scattering is really actually covering the entire thing. So I have two background regions you see right there, and you can see that so the two plots in the bottom, the red and the black one, that's from each background 1 and background 2, and the further away you are, the lower the background is, up until you reach about 20 keV, then the backgrounds are about the same. And the reason they're about the same is at that point, the source is gone. The source only has photons about out to 30, 35. So at that point, I'm no longer collecting source, I'm just collecting background. So the background is definitely depending on where I take it. So in the end, I had to go and do the NuSTAR background. I could not take a local background from the source itself. I had to take it from somewhere else. The other thing to check is the MLI. I mentioned this before, and I mentioned that it can be variable. We have corrections to it, but they don't always work. In this case, they didn't work. So there's the black curve you look there is FPMA, no MLI correction. The red is FPMA with MLI correction. The green is FPMB. So you can see that the green and the black agree, but where I have put the MLI correction on it does not agree. It overcorrects it. So in this case, I had to turn off the MLI correction in order to get the data correctly. So dust scattering. So dust scattering, you can use what's called XSCAT. So if you apply XSCAT, you can go look at that. It's actually very simple. The input there is really the distance to, you say, okay, there's a dust sheet somewhere here, and this is the grain type. And if you do that, you can correct all of these curves that are the spectrum. You correct the spectrum with XSCAT. So applying that, I could apply the correction and remove the dust scattering influence on the spectrum. So then I can derive halo intensity, size from that. Okay, now the spectrum itself, GX 13+1, is a complicated guy. And what you really want to do with all models is you want to apply a physical model, one that corresponds to some physical interpretation, in this case, COMTT, so you have a Comptonizing bulk flow. That's what other people had used. So we applied that, and we have all these features that you just cannot remove, or that the physical model is unable to account for. So that's very typical, and you do a lot of work and you just cannot remove them. And so in desperation, what you do is you apply what's called an empirical model, and you throw gaps. So these are Gaussian absorption features and edges at it to remove these bumps and wiggles in order just to make it flat. So you fit at a spectrum. It's not phenomenological, it is not physically motivated, but empirically you can make it flat. Now you shouldn't be doing this, but in some cases you need it to be flat because you have to do some things to it. So the other thing you want to do, and I said I wanted to use as a calibration source, so I had it at the same time with Swift and XMM and NuSTAR. So you can see there's the NuSTAR. This is just a time series. So NuSTAR, you'll see the dotted line, that's the occultation. Swift is also in low Earth orbit, so it also has just 2 and it has an occultation, and XMM had uninterrupted observing. Now we knew that this thing is variable. So if you have a variable source and you have multiple instruments, what you have to do is you have to do strict overlap of time. So you have to do these good time intervals where you're observing the source. That means in this case, if I had to compare all the spectrum from Swift, XMM, and Newton, I had to cut away everything from Swift and NuSTAR until they matched what's at Swift. So I had to really throw away all of the data in order to get it to match. And you thought, oh, well, great. Now I have the same data. And then you plot it all in XSpec and it just is all over the place. Just there's a tail there, it sticks up there. I have to say, this is not bad. I've seen it worse. Now, what I did, and this is, we do this, all of us do this, we start cutting away at the spectrum. So in the case of Swift, this is the red one. It had this tail that stuck up. And that's background, probably background. It probably makes sense. There's a good reason for cutting away Swift, ignoring it above 7 kV. In this case, I also ignored NuSTAR above 20 kV, and then I applied the phenomenological model, and this is what I got. The middle plot, it just doesn't quite fit. So what I then did is I had these cross normalization constants for each of them, and I let them float so that they each took different values. And you can see you got XMM sitting at 1. In this case, in NuSTAR then is 4% lower, Swift is 10% higher. That's perfectly within, that's within the cross calibration constants that we've measured before. So that's okay. So now I can kind of make them look at least somewhat the same. Light curves for GX13Y as a burster. So when I looked at the light curve here, you can see there's a burst there in the red box. And so I took a good time interval just with the burst itself and then compared it to the entire spectrum. And that's what you see in that little box below. You can see how different the spectrum is from the bursting itself. It's massively different. And I also did then a hardness ratio. So I picked different energy bands in the light curve. So I did light curves with 2 different energy bands. And that's what you see there, that in the low energy band, the soft energy band, the source did not change a lot. So all of the changes you're seeing, all the variations you're seeing was driven by the hot X-rays. That's the red curve you can see there. So you can see there was a lot of variation from the light curve itself and from the softness, the hardness ratio there. You can see that there's a lot of stuff going on. So then I extracted spectrum from each of the orbits individually. And here you see the plots of them, and they're quite different. They're quite different, but some of them are similar. So I collected the similar orbits together and then did fits of them, and that's the fits you see over there. So this is just to give you a flavor for how much you can do with this data, the different type of analysis you can do. And this source is filled with stuff. It is complicated, but there's a lot of stuff you can do. Okay, so bright sources are fun, but they are not easy. They can frustrate the hell out of you. And I've had this data set for a long time, and I've yet to write the damn paper because sometimes having too much, it's hard to actually give a good paper and get the right story out. And because their bright, complex details show up, and you have a hard time getting, maybe figuring out what is real and what is actually instrumental. But you have to realize also you can't get everything right. So at some point you have to make compromises, and you have to then be able to explain why you can't get it right. And that's the name of the game. So anyway, I'll stop here and take questions.
You say XMM, what do you mean? Yen, MOS, follow.
That was MOS, all of it. So we have MOS and PN. We had it in time. We had it going fast. Sorry.
I have a few questions. Can you go back to the page where you show the spectrum characteristics?
This one.
Yes. So first thing I want to say, when we usually join with FPM and FPMB, we add a constant to it that it takes care of. So I see that you have not used. Is there a reason?
Well, I didn't do it here because it's actually quite good. It was 99 or something. It was 0.1. It's sometimes you do it, but you don't always have to do it. In this case, it was unnecessary.
And the next thing. So here you said that you used the Gaussian because there was some noise kind of like to fit it phenomenologically.
Well, so these bumps and wiggles, right? They have They have astrophysical origin. We just don't have a model for it, except if you know how to run NuSTAR, and I do not. You can remove them, but so in lieu of that, so the reason why I hit it with an empirical plot, which does not tell you anything physically, but it does straighten it out, is because I had to do the dust scattering halo, and I didn't want to have all that feature there. So I had to just flatten it out, and I did that with the different Gaussian absorptions and edges just to remove the features that were left.
Well, my question is because the 6.4 is a very, prevalent line in many HIMARS and NOMA 60 bindings. So it could just be an iron line engine also. Right?
Yeah, no, it definitely could.
Okay.
I mean, it's just, yeah, it definitely could be. I'm not saying it's not, it has astrophysical origin, but if you just throw in a line, what you really want, and this, you'll hear this from Javier, RELZIL, these things that have everything built into them, which explains how all of it will, that's how you really want them to run. You really want the iron line to be tied to what the continuum is doing. In this case, you're just sort of fitting the iron line or whatever on top of whatever continuum is going on.
Thanks.
So let's go formula where the speed and channel
Mhm.
photon energy. So how will you exactly do those numbers like multiplied by 0.02 plus 1?
Yeah, so this is by design, right? The detectors work in PI channels, so first off, we calibrate them. Where it is? We calibrate them, and then we set that scale. So we said, okay, our low energy bound is going to be 1.6 kV. That's as low as NuSTAR goes. And then our resolution is 0.04. So each PI channel corresponds to 40 EV. So that's how, and we have 4,096 channels. So that's the number of PI channels. So you multiply that with the 40 EV, then you get your band, and then you have to shift it to where it starts, which is 1.6 kV. Was that your question?
Yeah, actually, I was not getting how, because these numbers are different in like different instruments.
Yes.
So
They are
this is
set.
based on the design.
Yes, it is instrument design. Each one decides what that is.
When we talk about, suppose we have a bright source and we are not able to put the background from the series, then we have to use the background from the provided by the NuSTAR usually.
Yes, so that actually, it makes you do work. You actually, there's a thing, it tells you how to do little things. It's not a fixed background. It'll derive a background. Actually, in the fitting model, it'll fit your background. It knows what the background model is, and then it'll fit one for you, and then it'll give you a background.
Is it a good idea to work with this sky background?
Yeah, so NuSTAR background it's a little hard to work with, not too hard, but if you can extract your own background, that's preferable, because it's not 100%. It's not as good as if you had the background locally, you're able to take it locally. But it's better than having no background at all. Right.
So does it provide any background? Sky background?
It does not. It gives you instructions on how. So it tells you to extract a little piece here and a little piece here, and then it will then use a model it has itself, and then it will scale the model based on your exact observation and give you then a background. So you have to do a little bit of work, follow the instructions there. So it's not like there's just a background and you take it. You have to actually do a little bit of fitting and work for it.
And you said, we have a source in one particular, they're writing 4 CCDs. In one CCD, and you said if there is no space, you can take it from the other.
Yes. Yes.
So, I think normally we should not do that. I mean, we don't prefer that because different like CCDs have different like contribution.
Yeah, so these are not CCDs. That's the first thing you have to remember. We're not talking CCDs here. We're talking they behave a little differently, and the instrumental background in them is slightly different. And this is, so sometimes you just don't have a choice. Sometimes you just do not have a choice and you have to go to a different detector. And so if you're above 20 kV, you're dealing with the background of the detector itself, the instrumental background, which is slightly different between them. So you can take the one next door. The background is not going to be quite accurate, which means that you should not be fitting all the way up to where your background crosses. You should be backing off 5-10 kV from that point. So that's, yeah.
Hi, I want to ask a bit about the dust halo study that you did. Did you actually see the rings in the NuSTAR?
No, NuSTAR doesn't show the rings, and because GX 13+1 is persistent, so it's always the same, not always, but it's pretty much the same intensity of flux. It just shows up as a bigger PSF, you know, it just goes off like kind of smooth. So you don't see the rings, unfortunately.
Why is the image prior to the master correction less distorted than after the master
Good
correction?
question. Yeah. So I was not gonna go there, but now that you asked, I will go there. Okay. So what happens? So we're on the dog again, right? You've got your detector sitting on the dog. Your optics is at the end of the tail. So in this case, and this is an actual, so you're sitting on the detector, you're sitting on the dog right now, and the spot looks fine. Now that 2 sits at the tip of the dog. So it did this. The mast itself did this because it was wagging back and forth. But you know, it was doing it tilting back and forth. And optics, when you tilt them back and forth, they don't change the direction of the spot, they just change the effective area. So so the detector up there, this is not a real detector, there's nothing at detector 2, this is just a transformation of the detector of the butt of the dog, what it looks like from the tip of the dog's tail. That's why that suddenly looks smeared out. When you then apply the sensor on the tip of the tail of the dog, which knows where the source actually was, it comes back together again. Did anyone understand that?
I did.
Okay, good.
Just going back to the background extraction. So in essence, if I can handle this around the source region and just keep shifting or expanding up until I find the cutoff. Can that be like the criteria from that?
You can. So I know for pretty much for XMM and others, they love annuli. We're not as fond of annuli because when you use an annuli, you end up on another detector quite often because the source is sitting very close here, very close to the gap. It's sitting very close to the center of detector, but it's on detector 0. So if you put an annuli around that, you are sampling detector 1, 2, and 3 at the same time. So this is why we are not as fond of annuli. You can do it. It just means your internal background is going to be a little wonky donk. But so this is a good, let's go back to the background here. So the background, I told you, oh, it's getting a little here. If you're below 20 kV, your dominant background is not the instrumental background. It is the aperture flux coming through, which is this ramp. You see the gradient. In that case, using an analyst is the right thing to do. If you're above 20, 30 kV, your dominant background is the instrumental background. In this case, you do not want to make an annulus because now you're sampling the other detectors.
I was looking at the slide where you have displayed the spectra from different missions. And I learned that unlike the models on NuSTAR, which are identical, the other detectors on those other missions may not be identical. Now, when it comes to modeling, do you have to choose different models to
Nope.
the same model?
So the same, so this is why things like ICES and XPEC are perfect. Well, they're good. So what they do is when you load each of these sources, they come with their own response files. So the software knows what is specific to that detector. So when I supply it with the same model parameters, and then each of these fits knows which files it needs to fold it through. So you don't have to, I mean, yeah, they could be wrong. The files could be wrong. And that's the whole thing with cross calibration. Now, I cannot tell you, and I should not tell you which one of these instruments is right. There are reasons why they all might look big. For example, NuSTAR has this tail that sticks up, and we've tried to figure out what the hell that tail is. I don't know why it has a tail compared to Swift. And sometimes it's there, sometimes it isn't there. Sometimes there's a tail in Swift. And I can't tell you which one is right. And so at some point you have to just go, you know, this is what I got. And yeah, do the best you can. And then also be honest about what you can't do.
Kristin, another one. In all your slides, you extract the background from a circle close to the source, more or less, which is actually something, you know, XMM, you know, we do with XMM data. However, you stress the fact that there is a space dependency of the background, and you also stress the fact that you are not limited in the shape of the background that you're using. So, isn't maybe sure you have thought about that in the team, but I was thinking a more natural choice would be I decide the circle from which to extract my source, and then I simply take the whole corresponding column of the detector as the background, because this probably minimize, depending on the orientation of the column or the rectangle, minimize the background radius. Is it a reasonable approach to be suggested rather than trying to guess where to put the circle around, which is always a degree of arbitrariness?
Yeah, so we don't have columns the way you have. I can't.
Well, not column, sorry.
Yeah, maybe I misunderstood.
I want to say rectangle around the circle.
Rectangle.
Essentially, you take this component
Yes. So
of your structure.
yeah, I'm trying to find where is that thing? Here. So here, let's take this one. So people do that, right? People do that. So what you're saying is that here you put your circle and then everything else here is your background.
For instance.
For instance, yeah, people do that. People do that. It's yeah, people do that. And I've done it too. In this case, making it simple. Circles are simple, but you can certainly.
Yeah, but my point is,
of course, the best thing to do is to exercise, but the fact that we use the circles as a default for the background is a bit of an opinion of mental inertia.
Well, we go back to this one, right? If we go back to this one, you have the problem is you've got the ramp. You've got the ramp across the entire detector for the background below 20 kb. So if you're below 20 kb, you don't want to take the entire detector because you're just sampling. For example, if your source is here, and you're sampling this. For the rest of your background, this is much higher than what you've got right there. So that is why a little bit of a thought. In most cases, I mean, if you're not certain, you just don't fit your source all the way up to where the background starts to dump and you just have to back off on it. That's the takeaway message. If you're not certain about it, just take a background as close as possible, as large as possible, without without the other constraints of cross another detector, and then back away from, don't fit all the way up to That's it.
I think that's.
Yes, I used up. See, I went short yesterday, so I used it all up today.